Welcome everybody, this is Nico from qutools, and today I'm going to bring you a webinar in cooperation with Quantum Design, giving you an overview of one of our products, the quED, the Quantum Entanglement Demonstrator. This is an experimental kit mainly intended to use as a demonstration experiment for university lectures or for use as in a laboratory course for advanced students. And in this webinar I'm going to cover the photon source we use, and tell you a little bit about how it works. We'll tell you about the control unit and the possibilities, and how you can expand your experiment suite with our add-ons. First, because it's the first webinar we give, let me tell you a little bit about our company. So we are qutools GmbH, situated in Munich in Germany, and since 2005 we want to develop quantum tools, as our name suggests, and just because we are very fascinated with quantum physics and we want to share that fascination with you. Our product lines include the educational tools like the quED, we're going to talk about that today, and the quantum coffer and the QNV, and we also have precision measurement tools for use in a laboratory like the qTag, time tagger, and the qDis distance measurement tool. So let's start talking about the entanglement demonstrator. It's the first real product of qutools. We have it since 2007, and in the beginning we had just one guy who was able to build it up to adjust the source correctly, and he had to work like for 2 weeks to get it done, and in the end he still had to hope that everything would work out fine. So we came a long way from that. We developed it very much further, and right now it's a very stable product. Everybody is more or less able to do it. As for the application, it's an experiment kit where you can do experiments with pairs of single photons which are generated in the source. You can do a small set of prearranged experiments. We describe them in the menu. You can have a look at our homepage if you want to. And as for the options, if you get your qED, you can choose to upgrade from a low rate version to a high rate version, where it will be easier to adjust everything, to align everything. And especially for the add-ons, I would recommend getting the high rate version. Also, depending on the application of yours, you can choose to get either manual rotation mounts like seen in the picture, or motorized rotation mounts for use with an automatic measurement suite included in the software in the control unit. As a technical description, I will begin by describing the optical part of the setup, especially the source situated in the white box. And after that I will talk a little bit about the possibilities of the control unit and how everything is connected. Let me first tell you a little bit about the source, and let me switch to our homepage for that, where we have a small animation showing everything. So in the beginning you need a laser. This laser emits light at around 405 nanometers and is focused onto a nonlinear BBO crystal sitting in the beam path. And when it hits the BBO crystal, there's a process called spontaneous parametric down conversion that can happen with a certain probability, which means that the pump photon will be split up into 2 down converted photons of double the wavelength, so half the energy of the pump beam. It means that the down-converted photons emerging from the crystal will have a wavelength of about 810 nanometers. And these are then coupled into optical fibers, and we lead them to the single photon detectors for analyzing what we have. This is the basic process, but actually in our setup it looks much more complicated, because we not only want photon pairs, but we want entangled photon pairs. And to get entangled photon pairs, it is not enough to use one BBO crystal, but we need 2. So let me explain these other 2 rows down in the bottom here. In the second row, we have the polarization. So you see, in this case, the photons from the pump beam are vertically polarized, which leads to horizontally polarized photons when they are down converted. And also in the fibers, they will look like this. The other thing you see here is the wavelength, so it's blue photons in front here and red photons in the back. And you'll see the spatial distribution, for example, in the fiber. It's a very narrow spatial distribution compared to outside of the fiber. And right down at the bottom, we have the Dirac notation for the polarization state of the photons. So, for example, here we have one vertically polarized photon denoted by V, and then down converted, this would be two photons, H, and also in the fibers. So to get entanglement, what we do is we insert another BBO crystal into the beam path. The difference between those two is that the optical axis of one of them is turned by 90 degrees in comparison to the other one. So the first one is 90 degrees rotated, which means that the vertically polarized light will not be active in this crystal. For light to be active in this crystal, you need horizontally polarized light. To get that, we insert a half-wave plate into the beam path that will change the polarization of the incoming light to V plus H, so to plus 45 degrees, because with this we have a superposition of both vertically polarized light and horizontally polarized light. So please notice it's still one photon, but it's now in a superposition between vertical and horizontal polarization, which means it can activate in the first crystal or in the second crystal. Please notice that these are not 4 photons in the back here, but only 2, with these two both happening at around 50% probability. So in the first crystal that was situated here, we convert the vertical part into these horizontally polarized down-converted photons, and in the other crystal we convert the horizontal light into this vertically polarized down-converted photons. In the fiber they will be at the same place. But we still don't have entanglement. Why don't we have entanglement? It's because we still can distinguish between photons coming from the are generated in this crystal and photons generated in this crystal. What we have to do is make them indistinguishable from one another. And we have 2 problems right now. As you can see, first, they arrive at different times at the input of the optical fibers. And secondly, they have a different spatial distribution because of the dispersion that is gotten by the photons originating from the first crystal. You see, those are more dispersed than the other ones. To compensate for that, we insert 2 other nonlinear crystals called IVO crystals or ytterbium vanadate. And one of them, called the pre-compensation crystal, will more or less see to it that the photons will arrive at the same time at the optical fibers, and the other one compensates for the dispersion effect. So as you can see now, the photons arrive at the same time at the optical fibers, and they have the same dispersion because the non-dispersed photons get a lot of dispersion in the second IVO crystal here. If you look at the polarization, you now have the vertical part and the horizontal part split up temporarily down here, so it's still one pump photon, but split up spatially, which means that now we have those at approximately the same position, but still a little bit apart and also differently dispersed. And after the IVO crystal and after the coupling into the fibers, they will be at the same spatial, in the same spatial mode in the single mode fiber, and also have the same dispersion. So we have this entangled state. You can see that by having this little box around this, which means that we now have to take into account both parties of the pair and cannot describe the system as a sum of the individual parts. So if I have all the properties of one photon on the one side and all the properties of the other photon on the other side, and just combine them, it's not going to be enough to explain every experimental outcome. We still have to account for the fact that this is a photon pair. Right, let's go back to the presentation and summarize that up a little bit. So we have on the left, on the right, there are the pictures with all the components we have to use inside our source to get it right. And just let me stress the fact again that the probability for this process is very low, so it's only 10 to the minus 11, which means only once in every 100 billion times the pump photon will be converted into 2 down-converted photons. So we need a very high power pump laser to get any photons out at all in the end. And to get an entangled polarization state, we need the coherent sum of 2 such processes, which means we need 2 BBO nonlinear crystals, we need 2 IVO crystals and a half-wave plate to get everything done. So how does it look in the actual setup? In the actual setup, it looks like this. This is in the white box when you get your experimental kit. So here's the laser, the pump laser. We have a lens in here and a lens there. These components just for beam shaping purposes. We focus the beam into this BBO crystal, which is the active component where the actual down conversion happens. Actually, in this plate, they are both crystals, and they are very near to each other and optically contacted, so it looks like just one, but it's actually 2 BBO crystals with the optical axis of one of the crystals rotated by 90 degrees with respect to the other. We have the pre- and post-compensation crystals inserted here as well. We have the wave plate that can be inserted, but could also be put in a parking position here. And we have some mirrors just to fold everything up. And on here, we have a pinhole where the pump beam has to go through, and also it's an alignment target you can use for an easier alignment. All of this sits in the white box, and in front, also inserted into the white box, is a long pass filter as a block for the pump beam. So if you have the white protective cover on the source, you don't have to worry about any safety laser precautions, because the high power pump beam will be only inside the box and not be able to come out. Only the down converted light, these red lines, can come out of the source, but those are of course of an intensity that is not dangerous to anyone. We then couple them into the fiber couplers down here by using the mirrors, and in between mirror and fiber coupler we can put polarizers to analyze our photons for their polarization. This is a block diagram of the control unit and all the electronics involved, and you can see here how everything is connected. So for example, the laser itself is connected via a normal serial cable to a laser driver, who just regulates the temperature of the laser and regulates the current you use. And then also from the optical part, 2 fibers will come out, and you can connect those 2 fibers to the single photon detectors situated in the box. Those will generate a TTL signal, which will be analyzed by the FPGA. All of this is communicating with the Raspberry computer, which will control the touch screen of the device, and with which you can communicate via network using the VNC protocol to copy the screen and put it on a beamer, for example, or use some simple HTTP code to control everything in the device. Maybe let me also note that you can of course save all measurement data on a USB stick. This is a list of the experiments you can do. The bold experiments will be are already described on our homepage and in the manual. The other ones are not described yet, but you can do them. So let me talk about how you can expand this suite of experiment you can do. We have at the moment 4 add-ons, and I will just briefly give you an overview over each of them. We have the quED HOM, which is a setup for seeing the Hong-Ou-Mandel Effect. We have the quED HBT to look at the photon statistics. We have the quED MI, which is a Michelson Interferometer, and the quED QKD, with which you can actually do quantum key distribution. Let's look at the Hong-Ou-Mandel setup. Basically, the Hong-Ou-Mandel setup consists of 2 fixed free space lines, where you just connect the signal input from the quED to the input fiber of the quED HOM to both sides. You have this free space line, which is then coupled into a fiber leading to a beam splitter, and after the beam splitter the fibers are connected to the detectors again. You can get this in a motorized version or in a manual version. I would not recommend using this setup with a low rate version of the qED. And it has to be matched to the qED, so if you want to get it at a later time, you have to send in your optical part of the qED, so we can match it to this add-on. With this setup, you can perform the Hong-Ou-Mandel interference experiment, which is a uniquely quantum phenomenon you can observe, and with no classical analog to that. The effect is the following. If you send two indistinguishable photons on the two different input ports of a beam splitter, then they will always leave the beam splitter together. You can see that by looking at the coincidences at the two output ports of the beam splitter. You can see them in the bottom, and at the point where the photons will hit the beam splitter at the same time, like here, the coincidence rate drops, because you only have a coincidence if the two photons leave the beam splitter at different output ports, and not when they leave the beam splitter at the same output port. For the HBT add-on, which is basically another detector module and a beam splitter, you can nicely see the particle nature of photons and analyze your photon source regarding the G2 correlation function. With our very compact design Michelson Interferometer, where you can adjust the path length by using a movable glass wedge inserted here, you can observe interference of single photons, and because of the insertable polarizers you can also do quantum eraser experiments or perform an interaction-free measurement. The quantum key distribution add-on consists mainly of an upgrade to the control unit, enabling you to pulse the pump laser, which means you can send single pulses with a pulse duration of 1 microsecond to 100 microseconds to use as a weak coherent pulse source for single photon pulses with an average photon number of less than 0. You can do that with a frequency up to 1000 Hz or just activate single shots for your measurements. Also, you'll get a wave plate which will be optionally motorized as used for Alice in the quantum cryptography experiment. You can actually analyze weak coherent pulses by use of the software, and you can perform the BB84 protocol with all the different classical and quantum steps involved, and generate a key to be used as a one-time PET cryptography. Also, because you can pulse the source, a lot of other experiments will improve didactically, because you can actually show what happens when you use single photons, like the particle nature of photons, a random number generation, or a single photon interference with the Michelson. Right, that concludes the overview of the qED. I thank you for listening. I hope I could clear a lot of your questions up today. And if you have further questions, you can of course have a look on our homepage at qtools.com/qed, or you could write to qtools@qdusa.com for further questions.